Welcome to another SRC webinar. This one is on the topic of blended refrigerants. We will look at their properties, some performance modeling considerations, and as well as considerations around coil design for coils running blended refrigerants. And we will look specifically in a little more detail at R-454B, which is attracting a lot of attention in the market as OEMs and other companies navigate the transition from R-410A and other HFCs. And to help us do that today, I'm joined by two folks from SRC. First is Jin Yu, our VP of Research and Development, as well as Ilya Kajan, who has the role of Sales Application Engineer at the Richmond Division. So welcome, guys. Thanks for doing this, and looking forward to it.
Thanks, Nate.
Thank you, Nate.
All right, so let's get right into it. Little overview of what we plan to talk about today. You can see some of the sentiments that I reflected in the beginning here, but we're going to focus on the background and timeline of some refrigerant regulation, some properties of R-454B, as well as just some general comments on blended refrigerant properties. Then we'll go over some testing methodology and the results of Jin's work in our two research labs on performance testing of R-454B in heat exchangers. And finally, we'll touch on some practical implications of those test results and sort of how the information that we learned from how the refrigerant performs can impact some design choices when designing coils and subsequently units and other systems. First off, like I said, our two presenters here, first, Dr. Jin Yu, VP of R&D for SRC. He has over 35 years of experience in heat transfer in the academic world as well as the private sector. He's authored 15 published works. Two more, I believe, are nearing publication as well. So we'll have to update that number in short order. And then Ilya Kajan, Sales Application Engineer for SRC, who comes to SRC from the refrigerated display case industry. So he has a lot of experience in thermal packaging, refrigerated display, like I said, as well as commercial HVAC coil design. And I'm Nate Budrick, Marketing Manager for SRC. I'll be moderating today's presentation as we go along. So, all right, so how did we get here? The background, some background and timeline of refrigerant regulation. As you can see, this has been really the history traces back farther than this to the 80s, I believe, with the Montreal Protocol, which was sort of the first, I would say, large-scale effort to regulate carbon emissions from refrigerant and related substances. And then you'll see the star showing where we are now. The two steps before that is sort of the big shift that caused folks to evaluate other refrigerants than 410A, which was the passage of the American Innovation and Manufacturing Act. And the big thing relative to this discussion that act did was it gave the EPA the authority to regulate HFCs, powers which it previously had not had. And in the time since that bill's passage, EPA has acted on that power by implementing new rules around the usage of HFCs with the plan of reducing the production and import by 85% over the next 15 years. There's a little bit more on some notable future milestones that are upcoming, the most pressing of which relevant to this discussion is probably that January 1 of 2025, which is effectively a moratorium on the manufacture of new equipment designed for R-410A. And so based on that regulation that we discussed in the last slide, the race is on, if you will, for organizations to develop plans for replacing 410A systems. 410A has long been a mainstay of especially the commercial HVAC industry. And to run through, I'm going to turn this over to Ilya to run through some of the compliant refrigerant options that are available for folks as they make that shift.
Yeah, thanks, Nate. Yeah, as we get closer to 2025, as far as our customers are concerned, we've seen three major options as replacement for 410A. Option one would be R32, which was initially a proprietary refrigerant developed by Daikin, but since then they've actually made it open source, so it's available across the board for any OEM manufacturer. Now R32 has a global warming potential of 675, and it's an azeotropic refrigerant, meaning that it's a single component refrigerant. Now, something like Carrier and Trains, they've actually decided to go a slightly different direction. They went with selecting R-454B. It's a zeotropic refrigerant, so it actually has a much lower global warming potential of 466. But the slight downside of that is actually blended. So it's actually 69% R32 and about 31% of R1234YF. And Jin will touch later on kind of the benefits and some drawbacks of that. And lastly, there is always opportunity to, quote, go the future-proof way, which would be the naturals option. And out of the current natural refrigerants that are available, it would be CO2, ammonia, or propane. And unfortunately, CO2 is the only refrigerant out of the three that has commercial viability, just because there would need to be a lot of building code adjustments in order to accommodate ammonia, which is toxic, and propane, which is highly flammable.
Yeah, and we've got some other content on the website and on our YouTube channel about CO2 and some of the barriers for its, I guess, mainstream adoption in commercial applications. Things like supply chain maturity are concerns. There's a lack of sort of established vendors for componentry like tubing and other things that are kind of proving prohibitive to sort of the quick uptake of that within a mainstream context.
Yeah, the jump to CO2 would be significant, but you are locking yourself in for a long-term system.
Right. And there's some education that needs to be done in the industry too regarding the pressures and other sort of operating conditions of the refrigerant. All right, and then so as you touched on, Ilya, there are the properties of R-454B are different from 410A, which is one of the reasons that we wanted to have this presentation and put some information on the refrigerant, on blended refrigerants out there, but specifically R-454B. As you said, there's the composition of it. The big one here, Jin, that I think you'll speak to in a few coming slides, and one that has been really, the concept of glide has been tricky for a lot of people to effectively understand and incorporate into their performance calculations. It means a lot of things to a lot of different people, but I think, Jin, you would, given your background, are probably among the most qualified to give it a little bit more context, which I think we'll do on the next slide. And a few more data points on the properties of R-454B there as well. And 410A, of course, which it is set to replace for a lot of applications.
Yeah.
Right. Jim, what are we looking at here?
Yeah, here we can. This is the phase diagram for the blended refrigerant R1234YF and also 132. So depends on the composition, particular R32 concentration. There's R454B, R454A, and R454C. So you
Jim,
can see.
Sorry not to interrupt, but you're saying that all three of those refrigerants contain some concentration of those two refrigerants, 32 and 1234.
Yep. Yeah. Okay. Basically, you can create it, a lot of more, but commercial available. There's three different types: 454B, 454A, B, and C. So you can see the difference is a concentration of the component. And this is a phase diagram for this blended refrigerant at 400 psia. So the far right side is 454B, and the middle is 454A, and the far left is 454C. And you can see there's a two line So one is called a dew point line, one is called bubble point line. So above dew point line is vapor phase. Below bubble point line is liquid phase. In between is two phase. So for single component, this two line is actually becomes a one. So when the phase change, there's no temperature change. But for the blended refrigerant, when there's a phase change in the process, you can see the two phase temperatures change during the process. So at the next slide, I can show you in detail what is difference between the dew point and the bubble point for 454B.
Got it. Yeah, and so basically the space between the blue and orange lines is the temperature glide for that refrigerant.
Correct.
Gotcha. Okay.
Correct. So this one show 454B, the glide. So you see for this particular blended refrigerant, there's a dew point temperature and there's a bubble point temperature. The difference between dew point and bubble point temperature we call the glide. For 454B, the glide is normally around like 2 degree at 400, which is very normal for condenser application condition. So the refrigerant inside the condenser actually start from vapor, which is from this phase diagram is above the blue line. And then when the temperature cool down, it's reached the dew point. So when the refrigerant reaches the dew point, refrigerant gets start condense. So, but because of this is blended refrigerant, during the condensation process, the refrigerant bulk temperature will decrease. Just follow the line. So from the blue line gradually down to the red line. So at the end of the condensation, the temperature of the refrigerant will be 2 degrees lower than the start.
And so
also, that's a fact. Yeah, that's a fact condenser performance because your refrigerant temperature lower by 2 degrees. And right. Also you can see at the start point, the liquid phase actually always follow the blue line. The vapor, I'm sorry, the liquid phase always follow the blue line. The liquid phase always follow the orange. So it means when they get start condensation, the vapor phase is at 454B bulk composition, but condensed liquid is moved to the right, to the left. So there's a more 1, 2, 3, 4, where F condense more than 32. Same thing at the end of the condensation, the vapor has more 32 than 1, 2, 3 F. So that's also the property of the vapor change during the condensation process.
Gotcha. Yeah, so I think that's good context for the added complexity inherent with R-454B as far as performance modeling that really wasn't there for 410A. 410A's performance profile is well understood, has been for quite a while, and so the difference there is what is driving a lot of this discourse in the industry about how to best approach these factors when designing new equipment. And then, Jin, primarily your role at SRC, there's a lot of research, obviously research and development it's on the business card, but part of which is setting up and conducting the performance testing that we use to gather and to validate, to gather data and to validate our performance model in our software. And so this next slide, and I know that that was a big project for you, and there was a lot of good work by you and your team involved in that. This next slide, we'll talk about, Jen, I'm going to have you speak to the background of that testing, how you conducted it, why you made the choices you did, and just some general information on it.
Okay. Yeah, to figure out the performance, actually figure out the characteristics of the 454B condensation, the evaporation inside the tube. We did several different tests. First, we have a tube side heat transfer lab. We did not show the picture here. We test 454B inside the tube. Under condensation and evaporation. So we using those data, we're going to we validate the existing formula for tube side heat transfer coefficient formula. Also, we use this wind tunnel lab to test multiple condenser and the evaporator with a 454B. And so we gather a lot of data under different conditions. So those tests, we use a different coil. So we cover different tube OD, the different inner surface, either smooth wall or either rifle tube, or we have a different die pattern check it. During the test, we also change the refrigerant flow inside because we know the flow mass velocity inside the tube, inside the coil will be a very important factor. So we vary that, and we also we can change the pressure. We can change the superheat. We can change the subcool for the evaporator and condenser. So we test, I believe it was more than 2,000 of coil, and we got more than 100 points of data. So we can validate our selection program and twist our model as well.
Great. Yeah, thanks for that background on sort of the how we did it. And then as a result of all of that testing, this next slide talks about essentially what we learned about the performance profile of 454B relative to 410A. And there's some headlines, I think, that you took away from those tests, from that test data, that are certainly going to be of interest to some folks in this audience. So I think first, could you give just a brief explanation on the difference between coefficient of performance, which is COP there, versus capacity?
Yeah, this is normally there's a two-way to evaluate the impact of a refrigerant on the system. So if you're talking about the efficiency of the system, most people would like to use a COP. So COP is a ratio that you get versus you pay. So how much BTU you get versus how much power you put. So, and then the other way you can evaluate this impact of 454B is capacity change. This is we saw from our testing, also from our analysis. So 454B, if you evaluate the system based on COP, you can see 454B slightly higher than 410A on the COP side. But if you're talking about capacity, so for same system, I'm talking about have same evaporator and condenser and the same compressor, whatever. So 410A will win the game. 454B, we see it always has a less capacity for if you want to do some kind of drop-in replacement work.
And we want to be clear in this slide, as well as subsequent slides for the remainder of the presentation, that the claims we're making and the observations that we gathered from our testing, these, like the 10 to 15% additional heat transfer surface, these only apply to OEMs or customers that are planning to bridge the performance or the capacity gap between 410A and 454B with a coil redesign. There will be applications where the performance gap, depending on conditions, will be less severe. And so it could be entirely possible, and likely is for a lot of applications, that the performance gap can be bridged using some other componentry adjustments or changes to things elsewhere in the system. But this pertains only to the coil level of the unit.
Mm-hmm.
Yeah, so I read this to say that there are definitely applications where a drop-in replacement of 410A with 454B will not work. It will not meet requirement. Is that fair to say?
Yeah, we're not meet the capacity requirement, but a lot of case study shows, drop in, you will get more COP, means efficiency of the system, means you get less capacity, but you pay less, power to the system.
Got it.
Because of the nature of the refrigerant.
Yeah, and I think so we landed on that. You'll need 10 to 15% additional coil surface to bridge that capacity gulf while still enjoying the better COP.
Yeah, particular for condenser, because you lose a 2-degree delta between the refrigerant and the air. So yeah, you need to prepare the more surface area for a condenser, particular.
Yeah, so that kind of pivots our conversation from the concept of glide from a theoretical standpoint, and now we're getting more into the practical implications of what that temperature glide looks like as it manifests in actual system operation. And so, and to further that practical consideration discussion, we ran, Jim, this is what you were talking about with the identical coils. So these are effectively the same coil, same operating conditions, run with each of the refrigerants that we're talking about in this presentation. Do you want to just sort of run through what you're seeing here and some points that you think people should know about this exercise that we did?
Yeah, actually, this is a real work we did for our customer. The first, the left side is original design for 410A evaporator. So the coil, you see the airflow and the required BTU, and the evaporator temperature is 60 degree. Suction temperature is 60 degree, and the liquid temperature is like 125. And same coil, 46 by 70, 4-row, and we use a 3/8 tube and 16 film per inch corrugated surface. So for this configuration, this size coil with the 410A, you see the rated capacity is 195,000 BTU. So this is already used in the customer system. It's approved. And we use our validate software. We rated as a 454B with the same size of coil, same configuration. So you see airflow the same, air temperature same, and suction temperature is the same, liquid temperature same, and the coil circuit is the same. The exact same coil, exact same condition. The coil only performed 182,000 BTU. So this is show why. If you change the refrigerant from 410A to 454B, you're facing a short capacity if you don't replace the coil.
Yeah, understood. And then from like an OEM perspective or a unit manufacturer perspective, that means that, with the deadline for, there's a moratorium approaching on the manufacture of new equipment that is designed for 410A. So as part of that process, there's an opportunity for, because I think we've established in theory and practice that a direct drop-in is just not for a certain, like, significant amount of applications or scenarios is not viable. And so that then leaves the questions of, so what do you do? How do you make up that capacity discrepancy? And so this next slide, and so we said that it was a matter of heat transfer surface area on the coil. And so this next slide talks about some ways that you can, without drastically increasing the footprint, so that, you know, your additional components of your unit don't have to, you know, substantially change, but there'll be tweaks here and there, of course, but without drastically increasing the footprint of the coil. These are some recommendations that we would make as coil manufacturers, and specifically as Ilya, this is the kind of conversations you have with customers every day. So why don't you take this slide and just run through some of the, like, these bullet lists here to show that some recommendations that we would make and some of the implications elsewhere in the system, because as we talk about seemingly every day, coil design and heat transfer is usually a study in trade-offs.
Yep. Yeah, for sure. So it really just depends on the manufacturer, right? So some manufacturers have an established cabinet size and they want to keep the coil footprint the same. And in those scenarios, you know, we would try to make up the capacity difference by we could increase the fin density, which would increase the heat transfer area and potentially make up for the capacity lost. We could also go and alter the fin geometry for the aluminum fins on that coil. So for example, if you're using a flat fin geometry, we can go to something slightly more aggressive like corrugated or sign to address the capacity loss. We also had some manufacturers that increase the RPM on their fans, so effectively increasing the airflow through their coils, which aids in the capacity loss. And we also have some manufacturers that really took this industry-wide change to refresh their cabinet portfolios, in which scenario we have a little bit more an opportunity to play with coil size and coil dimensions if it's important for them to keep fin spacing or fin geometries identical to what their existing coils are. So there's really two sides to this story, and it really is in the ballpark of our customer of how they want to approach it, whether they want to keep it as much as possible the same, or if they're going to take this as an opportunity to refresh their cabinet portfolio.
All right, and so Ilya, on these next couple of slides, we ran some enterprise selections that incorporate some of these changes in an effort to bridge that capacity gap. And I'm going to have you walk through a couple of there's a few call outs here, but just speak some to exactly what the implications of making some of those recommended changes would be.
Yeah, so in this particular case, the customer wanted to keep the footprint of the coil the same. So if you remember from the original 410A run, they were actually using corrugated corrugated fin geometry. Whereas with this one, they went slightly a little more aggressive to sign. And just by altering the fin geometries, we were able to make up a lot of the capacity that was lost. So effectively went from about 182 BTU per hour back to just slightly under 195 BTU an hour. And the downhill implication of that is the air friction went up slightly. So we went from about 0.31 water column to 0.4. So those are just one of the trade-offs that you're looking at while trying to keep the coil size the same as the original 410A coil.
And that increase in air friction, that's going to affect power consumption. Is that correct? Is there anything else?
It's going to affect power consumption directly coming from your fan motors. Yep. So your fans are going to be working slightly harder now. Gotcha.
All right. And then for this next one, this is just for a customer that might have a little bit more wiggle room with their cabinet profile.
Yeah. So this was kind of the other the other side of what I was alluding to with some certain customers taking this opportunity to rebrand or refresh their cabinet portfolios. And in this scenario, we kept everything the same. There was opportunity to make the coil slightly longer and bridge the capacity gap that way. And when you do things like that, you're actually lowering your air friction, which helps your fan motors in this scenario run more efficiently.
All right. Thanks, Ilya.
Mhm.
So that sort of wraps up the practical side of things of the what do we do with this test data and these differing performance profiles of the incoming versus the outgoing refrigerant 410A. And then for this next bit here, all of this is to say that, and all of the data that Jin and his team have added into or have gathered from their testing, that data is used to, as we said, to validate Jin and his team's performance modeling for that refrigerant, the formulas and the calculations that they use to spit out a number when a customer inputs their data into Enterprise. And Ilya, from a customer standpoint, maybe just speak a little bit about Enterprise, how it works, why it's useful for customers to be able to have the ability to rate this new refrigerant in our selection software.
All of Jen's really good work in the Wind Tunnel Lab really went to update our enterprise software. So usability, it remains the same. And the way our customers would rate the coils remains the same. So nothing scary there, but we do have proven test data in order to validate our models. And this really allows our customers to get their hands dirty and size their own coils. But if there are issues, when it comes to performance and temperature glides and any sort of concerns out there, we are always available to answer any questions and really help out with new coils designs and cabinet refreshes.
Awesome. Thanks, Ilya. And yeah, just to round out what you were saying, these are some of the folks that you'll want to contact if you do find you and your team are having these conversations about, as we all sort of get further down this transition path. And I think with that, we are going to go ahead and call it. Jin, Ilya, appreciate the time again. And yeah, for anyone watching, feel free to reach out if you have further questions. But I think that's going to do it for today. Thanks, guys.
All right. Thanks, Nate.
Thank you.